Okay, ladies and gentlemen, let's talk about this cubic homework, okay? So the first problem I gave you was y equals x cubed plus 1. I asked you to give me the t-table, the graph, and the transformations. So let's do them one at a time. So first we've got the t-table. 1, 2, 3, 4. So we treat these the same as we treat everything else. We are looking for an h and a k. Do you have an h? I don't see any parentheses, so no, I don't have an h. So my vertex is 0. And what's my k? 1. So I start with 0, 1. Then I work down 2, and I work up 2. If I plugged in, I don't know, let's start with negative 2. If I plugged in negative 2 here, what's negative 2 to the cubed power? So negative 2 to the cubed power, that means negative 2 times negative 2 times negative 2 plus 1. Negative 2 times negative 2 is positive 4. And then positive 4 times negative 2 gives me negative 8 plus 1. And then negative 8 plus 1 gives me negative 7 for my value there. Please keep in mind that when you cube a negative number, it stays negative. 2 times 2 is 4. 4 times 2 is 8. That's how you do that. Let's talk about if we plugged in negative 1. If I cubed negative 1, then added 1, negative 1 times negative 1 is positive 1, and then positive 1 times negative 1 keeps me at negative 1 plus 1, that gives me 0. If I plug in a positive 1 here, 1 cubed plus 1, well, 1 times 1 times 1 is just still 1, plus 1 gives me 2. And then if I plug in a 2 here, I end up with 2 cubed plus 1. 2 cubed is 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. So this is going to give me 8 plus 1, and that gives me 9. So here are my lovely points. So that checks off number 1, the t-table. Now we graph. So my lowest value looks like it's 7, and my highest one is 9. I don't have enough room to go that high, so I'm just going to guess when I get too high or too low. So my first point is left 2, down 7. So 1, 2, down way down here somewhere. My second point is left 1, and then I don't go up or down. My third point is stay there and then go up 1. My fourth point is go over 1 and then up 2. And my last point is to go over 2 and then up way up here somewhere. And if I trace all these lines and I go, ooh, and I end up with a squiggle squaggle. And that's where I get my shape from. So transformations, we do the same way we did with quadratics. Do I have a here for a vertical stretch or compression? No. Do I have an H for a horizontal shift? No. Do I have a K for a vertical shift? Yes, I do. So what's my vertical shift? It's a vertical shift. We moved up 1, right? Plus 1, up 1. And that's it. Let's look at number 2. Number 2 was y equals negative x minus 1 cubed. So negative x minus 1 cubed. Looking at my original problem right up here, do I have an h? Yes, I do. Do I have a k? No, I don't. So I already know that. Do I have an a? No, I don't. Do I have a negative? Yes, I do. So that's going to change the shape. Remember what we said? If the line is going like this and it's negative, it's going to flip like that. If we have a parabola, it's going to flip like that. It's going to change the shape. So if it doesn't change, we know something's wrong. Let's do our t-table. One, two, three, four. Okay, what's my vertex? My vertex is hk, so h is -1. We switch that sign always to a +1. That's a +1. It's a little messy. And then we don't have a k, so it's 0. So from +1, I'm going to go down 2. So 1, 0, -1. And then I go up 2. 1, 2, 3. And then I'll plug in each of my numbers. So let's say I had a -1 in here. So I had a -1 minus 1 cubed. Well, what's -1 and -1 together? -2 cubed. What's -2 times -2 times -2? That's -8. And then -8 gives me +8. That double negative might give you trouble. That's why I made this a homework problem and not a quiz problem. It's tricky. What if I plug in a 0? 0 minus 1 cubed. What's 0 minus 1? -1. What's -1 cubed? It's -1. What's double -1? +1. What if I plug in a 2? I end up with -2 minus 1 cubed. What's 2 minus 1? 1. What's 1 cubed? Still 1. So I end up with -1. And what happens if I put a 3 in here? 3 minus 1 gives me 2. 2 cubed gives me 8. And then I get -8. So I have very clearly run out of room here. So I'm going to have to move to a second page because I have big handwriting. So graphing this, looks like I go up 8. So I'll try to get all the way up there. 1, 2, 3, 4, 5, 6, 7, 8. Just barely. 1, 2, 3, 4, 5, 6, 7, 8. Great. So my first point is left 1, up 8. Left 1, up 8. My second point is stay there, go up 1. Third point is go over 1 and then stay there. My fourth point is go over 2 and then down 1. My last point is to go over 3 and then down 8. And if I trace this, squiggle squoggle, I end up with that. Now, does this look inverted from that negative sign from the other one I did? Yes, it does. So I think I did this one right. So, what are my transformations? Well, the negative means I have a reflect over the x-axis, and the -1 here means I have a horizontal shift. It's changed from negative to positive, so it's to the right one. And then I have no other numbers here, so it looks like that's it. All right, so number 3, y equals 3x cubed minus 3. So step 1, what is my t-table look like? 1, 2, 3, 4. I need my vertex, which would be h inside parentheses. I don't see any parentheses, so that's going to be 0. -3, that's k, I keep the sign. So now, from 0, I go down 2, so 0 minus 1 is 1, 0 minus 2 is 2, 0 plus 1 is 1, 0 plus 2 is 2. Now I have to take these 4 numbers, the ones in pink, and I have to plug them into this equation. So step 1 is -2. 3 times the quantity of -2 cubed minus 3. What's -2 cubed? -8. So 3 times -8 minus 3. What's 3 times -8? -24 minus 3. What's -24 minus 3? -27. That's a big old fat number. We're definitely not going to fit that on our graph. So the next one is -1. So 3 times the quantity of -1 cubed minus 3. What's -1 cubed? It's still -1. So what's 3 times -1? -3 minus 3. What are two -3's combined? -6. Fourth one, we have +1. 3 times the quantity of 1 cubed minus 3. What's 1 cubed? 1. So 3 times 1 minus 3, that's just 3 minus 3, that's just 0. Last one is 2. 3 times the quantity of 2 cubed minus 3. What's 2 times 2 times 2? 8 minus 3. 8 times 3 is 24. Minus 3 is 21. Alrighty. Got some crazy points this time. For sure. And I'm definitely not fitting all of those on my graph. But that's just fine. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. My first point. Left 2, down 27. So I'm going to have to really guesstimate here. Left 2, down really far. I'm just going to draw it down there. Left 1, down 6. 1, 2, 3, 4, 5, 6. 0, down 3. 1, 2, 3. Over 1, stay at 0. And then positive 2, 21, way up here somewhere. If I trace these dots, squiggle, squiggle, I end up with that. Why is it such a tall boy? Because this 3, what is this 3? It's our A value. This is a vertical stretch by a factor of 3. It's 3 times as tall as a normal one. That's why it's so tall. Do we have a horizontal shift? Nope, nothing in the parentheses. Do I have a vertical shift? Yes, I do. And it's down 3. Finally, number 4, we had y equals 1/2 x cubed. So 1/2 x cubed. That's janky, but we got to do it anyway. So make my table. 1, 2, 3, 4. What is my vertex? Do I have an h? No, no parentheses. Do I have a k? No, no numbers out here. So my vertex is 0, 0. I go down 1, then I go down 2, then I go up 1, then I go up 2. So I got to plug in these 4 numbers. So let's just do it. 1/2 times the quantity of negative 2 to the third power. What's negative 2 to the third power? It's negative 8. What's half of negative 8? Negative 4. How about negative 1? 1/2 times the quantity of negative 1 cubed. What's negative 1 times negative 1 times negative 1? It's still negative 1. And what's negative 1 times 1/2? We just get negative 1/2. What about positive 1? 1/2 times the quantity of positive 1 cubed. Well, positive 1 cubed is still 1. What's 1/2 times 1? It's 1/2. And 2. What's 1/2 times 2 to the third power? 2 times 2 times 2 gives me 8. And then 8 times a half of 8 is just plain old 4. So, when I graph this, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. My first point is left 2, down 4, so left 2, down 4. My next point is left 1, down a half, so I'm going to put it somewhere between these. My third point's the origin. My next point is over 1, up a half. And my last point is over 2, up 4. When I trace these, I end up with a cute little squished down parabola. Now, why does it look so small? Because I've got a special little number 1/2 here, and that 1/2 is doing something special. What is the 1/2 doing? It is a vertical compression by a factor of 1/2. And I have no other numbers, so there is nothing else going on. There is the algebra homework. I hope you got it. If you didn't, we're going to be using Wednesday as a review day to review linear, quadratic, cubic, and square root functions before we sort of quiz on all of those. But for the homework, I gave you these 3 problems. Number 1, I based this one off of 12-8 on page 322. I said, what's the boiling point of benzene when 0.75 moles of phenol is added to 1 kilogram of benzene? And I gave you the boiling point elevation of benzene. So we have an equation. It's the change in boiling point elevation equals that good old-fashioned molal constant times the molality. And so what have I been given here? I have moles of something. I have kilograms of something. Hey, moles and kilograms. I remember that from somewhere. That might come in handy. And I gave you the constant for benzene. So I know I have the constant. So let's go ahead and plug that constant in. I said Kb is 2.53 degrees Celsius over molality. Now I still have to fill in this m. So what did m stand for? Do you guys remember? M was moles per kilogram. And before I say something dumb, yeah, it's moles per kilogram. Whew, I had a brain fart there. So if this is moles per kilogram, how many moles did they give me? 0.75. How many kilograms do I have? 1. What's 0.75 divided by 1? That's still 0.75. So I have 0.75 m in here. So now I multiply. What's 2.53 times 0.75? I got 1.897. And I'm going to shorten that to 1.90. My m's cancel out, so 1.90 degrees Celsius. So this is an important answer, but it's not the answer. Because I didn't ask you what's the boiling point change. I asked you what's the boiling point period. So what I'm going to need to do is figure out, well, what's the boiling point normally? Because I just changed it. And to do that, I would look in this handy little table right here. What's the boiling point of benzene? Well, it says the normal boiling point of benzene is 80.15. So my normal boiling point is 80.15 degrees Celsius. I'm increasing it by positive 1.90. So what's my new boiling point? It's 82.05 degrees Celsius. Hooray, that is my new boiling point. Number 2, I based this problem off of example problem 12-9. If 315 grams of calcium bromide are added to 610 grams of hot water, what is the boiling point? So, I have grams, and I don't really want to use grams. If my equation is the change in boiling point equals that constant, which is Celsius over molal, in molality, which is moles over kilograms, then I'm going to have to change some of this stuff. So, what do I have? I have something here and something here, right? One of them is going to be a solute, one of them is going to be a solvent. Which one's usually bigger? The solvent. So which one's going to go in the bottom? The solvent. So I'm going to have 315 grams of calcium bromide over 610 grams of hot water. Some hot, high-quality H2O. So I'm going to need this to be in moles over kilograms, because that is the units of molality. So first off, how would I get the bottom into kilograms? Well, if it's in grams now, and I want to get to kilograms down here, how many grams are in a kilogram? 1,000. Yay. Okay. So, oh, I'm sorry, that was silly. It's grams. So my grams are going to cancel out. Yeehaw. So now the bottom's good. I need to get the top into moles. 315 grams of CaBr. How the heck do I get that into moles? Well, if I want to get to 1 mole, how have I done that since stoichiometry? Well, I divide it by the molar mass, right? So what's the molar mass of calcium bromide? I got 199.89 grams. So these grams cancel out. So it's looking like what I'm left with in the top is 315 times 1,000, which gives me 315,000 over 610 times 199.89, which is 121,932.9. Big numbers here. When I divide this up, 315,000 divided by 121,932.9, I get a grand total of an unimpressive number, 2.58. It's asking for what's the boiling point. It's 2.58. On the top, I end up with moles as my units. And at the bottom, I end up with kilograms as my units. The whole point of this was because moles per kilogram is in the unit of molality. So I have 2.58 molol. Oh, that's off the screen. I have 2.58 molol. So it's asking what's the boiling point. The reason I was doing that was so I could plug it into my equation up here. So, what is my change in boiling point? Well, I'm using hot water, so what is the boiling point of water? I gave you that in your notes. It's 0.512 degrees Celsius, and that is being multiplied, I'm out of room. That is being multiplied by the number we just got, which is 2.58 mole. So when we multiply these numbers, we finally get our answer after some good old-fashioned stoichiometry. And I am getting the number that the change in boiling point was 1.32 degrees Celsius. And for sake of sanity, I'm going to stop there. But if you wanted to actually finish this out, you could say, well, what's the boiling point of hot water? You would take the 100 degrees Celsius, you would add your new number, which is 1.32 degrees Celsius, and you would end up with 101.32 degrees Celsius. That is your new boiling point. When I did the problem, I meant to write that as what's the change in boiling point, but anyway, it's one extra little step. Last problem. Number 3, which I based heavily off of 12-10. What is the molality of a solution of aluminum trichloride in water if the solution has a changing boiling point of 6.50 degrees? So, what's my equation? Change in boiling point equals the molal constant times molality. What am I looking for? I'm looking for molality. So I would rearrange this equation. How do I get m by itself? I divide both sides by kb, and I end up with m equals the change in boiling point over kb. All right, so what do I have? I have the change, right? The change is just 6.50. So I have 6.50 degrees Celsius over, what is my constant for water? I just used it. It is 0.512 grams. Oh, I'm sorry. Degrees Celsius. I misread my own heading. Degrees Celsius molality. So when I simplify this, 6.50 divided by 0.512, I end up with 12.70 moles per kilogram. And there's my answer. All I had to do was plug the numbers into my equation. There's the homework. Tricky, but I tried to keep it fair because the problems were so very similar to the ones we did on the video. We've been moving at quite a fast pace in chemistry, and I'm not unaware of that. So to be fair, I think that instead of having a quiz on Wednesday, we will probably have a review on Wednesday of what we've covered, and then do a quiz on Thursday, just to be fair. But with that being said, I wish you all a good day and good luck